Today we are going to be looking at balancing equations. Now, before we get into dealing with the ratios of numbers which can be manipulated either on the left-hand side or right-hand side of a reaction and trying to balance an equation, first I want to look at the very basics. I just want to recap over the very basics of a reaction, of a chemical reaction. So let's start very simply. Let's say we have got A here reacts with B to give us C and D. So we have a very straightforward reaction here. A plus B equals C plus D. So we can say this in this forward reaction we have at least 4 different types of components that we have to be aware of and dealing with. Now, how do we identify or label, let's say, components A and B? Components A and B, as you all are aware of, are called reactants. So we can identify components A and B as reactants. Components C and D are known as products. So these are your products. Now the arrow represents a forward reaction. This may not always be the case, as you can also have a backward arrow representing a reversible reaction. However, for time's sake, we are just going to deal with forward reactions, but just be aware you can have a backward arrow or halved arrows representing a reversible reaction. So we've identified our reactants and products. Now, if I was to put certain numbers in association with A, B, C, and D, we then have to identify these numbers and give those numbers a label as well. So I'm just going to put a 2 here, and I'm going to put, let's say, a 3 here, and let's say we put a 4 and let's say a 2 here. Now this equation is not balanced, and we are not trying to balance this equation. At this stage, I just want you to know what the different components of a general chemical reaction or chemical equation looks like and how we identify it. So these numbers in green, we need to be able to identify those. Now the big number is called a coefficient. So these numbers in green, the big numbers, the 2 and the 3, these are called coefficients. So this is a coefficient there, and this is another coefficient. Okay, so they are this is how we will start manipulating the equation in terms of ratios later on. And the smaller numbers, these represent the number of atoms that A or B represent. So they represent the number of atoms. So just going back to the coefficient, because this is where most students will struggle with in terms of when they come to balance the equation. Just remember that the coefficient represents the relative numbers of reactants or products, and they are placed immediately before. So on the left-hand side of each formula, as you can see, the 2 is before the B, the whatever element B is representing. And if you have a coefficient of 1, by practice, it is omitted. We do not include a coefficient of 1 in our chemical equations. If you're omitting the number, you are telling the person that there is one coefficient there. Here we have represented the coefficient 2 and 3. But for A or for C, we have not represented the coefficient. That means we are telling the examiner that that is 1. Okay, so by omission in a chemical reaction in chemistry, by omission of the coefficient, we are telling the person, whoever is reading the reaction, that there is 1 there, the coefficient of 1. In terms of the reaction, so let's look at CH4 plus O2 goes to CO2 plus H2O. So we've got our reactants on the left-hand side. We have our products on the right-hand side. Now, here I'm just going to quickly balance this out. So we'll come on to the steps later. But as you can see here, the coefficient of 2 is how we represent it in front of the element symbol. So we've got a 2O2 there, and then we've got 2H2O. Now, whenever we write chemical equations, another important step, let's put this in another color, another important step is to make sure that we have our state symbols. Generally, it's a good practice to get into the habit of putting state symbols down for a particular product or reactant in a chemical reaction, in a chemical equation. Now, in terms of what we're doing here, actually, I won't put the state symbols here directly because it will get complicated when we start doing that and we're mixing everything around. But generally, just be aware that state symbols will be needed. Now, actually, let's do it. Let's put gas. Okay, so methane is your gas, oxygen is a gas, carbon dioxide is a gas, and water is a liquid. So we have our state symbols here, and then we have our coefficients. So this is how a typical equation, a chemical equation is represented. You have the coefficients here, and you have your products. You have your products on this side, and you have the reactants. Okay, so this is how a chemical equation would look if it was represented via an actual reaction, as we see here. I would like you to note that though I have explained the large numbers in front of the elements or the compounds in the equation as coefficients, the coefficients represent relative numbers. Therefore, you can also view these coefficients as ratios. So if we look at this chemical equation here, we can get a ratio of 1 to 2, and if we move across, we can also get a 1 to 2. So the ratio that the simplest ratio that we can identify here is 1:2 and 1:2 again on the product side. Now, the practice is to get the smallest possible whole number coefficients in your chemical reaction. So just bear in mind, you're always trying to get, when you're balancing equations, the smallest whole number coefficient. Now, this equation here could very easily be represented in another way. We could also represent this, but it's not the best practice and it's not the way I want you to balance your equations. You could multiply these numbers up and you could represent, let's say, 2 to 4 2 to 4 and 2 to 4. But bringing it down again, it would still give you 1 to 2 and 1 to 2 on the reactants and product side. So just be aware that your aim when balancing equations is to, and the common practice is to use the smallest possible whole number coefficients in your chemical equation. This equation again. So we have CH4 plus 2O2 gives us carbon dioxide plus water. Now, if we balance this again, so we make sure it's balanced. Now, this equation can be, let's say, explained in a number of ways, and this is where students tend to get confused. Now, I'm going to explain this equation in 3 different ways. And I want you to listen to each of the 3 different ways and understand they essentially mean the same thing. So if you get an exam question where the key words are throwing you off, you need to be aware that if it's amongst these 3, essentially we are talking about the same principle. So this equation can be represented or explained in the first way. 1 methane molecule and 2 oxygen molecules react to yield 1 carbon dioxide molecule and 2 water molecules. You see, that's the first way. Second way, 1 dozen methane molecules and 2 dozen oxygen molecules react to yield 1 dozen carbon dioxide molecules and 2 dozen water molecules. That essentially was the same as the first one, except we're using slightly different terminology. But this third one is where I want you to pay particular attention, because this comes down to the concept of the mole. Now, 1 mole of methane molecules and 2 moles of oxygen molecules react to yield 1 mole of carbon dioxide molecules and 2 moles of water molecules. So this is an important distinction here. Not a distinction, but something to remember. It's not different to what we've just learnt. It's just another point to remember in terms of how to view chemical equations. These numbers can be explained as being moles. Okay, they have a molar value there. Okay, the large numbers. Notice I'm not identifying the smaller numbers, such as the 2 in front of the hydrogen, or the 2 in front of the oxygens, or the 4 in front of the methane hydrogen. I'm only referring to the large numbers here, the bigger number, the coefficient. And this is 2 moles, this is 2 moles, and here we would have, because by omission it's the same principle, we would have 1 mole there. It's just another way in which we represent a chemical equation. Okay, so it should be, I should write 2 moles here. We can just make this a bit more clearer, a bit more. So we have 2 moles there, 2 moles of oxygen, 2 moles of water, 1 mole of methane, 1 mole of carbon dioxide. The whole aim of balancing equations is to obtain an equal number of atoms for each element involved in the reaction, where there is an equal number represented in the product side and in the reactant side. So I'll repeat again, an equal number of atoms that are involved in the reaction in the product side and the reactant side. Both must equal out. This is the conservation of mass. This is the law of conservation of mass. and all our chemical equations must be consistent with the law of conservation of, not mass, matter. So the conservation of matter states that whatever you have on the reactant side must be equal in the product side when we are dealing with each individual, when we're dealing with the number of atoms on the product, on the reactant side and the product side. So when we balance an equation out, we can see that this equation is balanced, and we have obtained this by manipulating the coefficients. Notice that I have not yet mentioned anything about the smaller numbers, the subscript numbers. These numbers, I have not ventured into these numbers yet. Now, when we come to balancing equations, you cannot alter the subscript. So you must not alter the subscript numbers. And this is very important. You can change the coefficient, and all it does is change the amount of the identity of the particular reagent. And I'll repeat again, you must not change the subscript because it will change the identity of your particular reagent or product. Now this is an important point here, because by changing the coefficient, you are simply changing the amount of the substance. But by changing the subscript, you will change the identity of the reactant or product. For example, if we take H2O, so let's take H2O. Now, the subscript here is 2. Now, we have balanced it by changing the coefficient to 2 here. This changes the amount we have. However, if I was to change the subscript, i.e. try and balance this equation out by changing a subscript, and let's say for argument's sake, I put H2O2. Now, we do not have water. This is not water. This is no longer water. Okay, so we can't do this. This is an entirely different compound now. It's not water. However, we can have 2H2O, we can have 4H2O, we can have 6H2O. All of this is still water. So this is very important, because students sometimes get confused when they start thinking about balancing chemical equations, and if they haven't done enough practice questions, they are confused as to whether they are allowed to change the subscript or not. So just remember, you must not under any circumstance alter the subscript, i.e. the smaller numbers. Let us do a worked example. We'll do 2 worked examples, and then we'll go straight through with 3 more quick balancing equations. So the first example, so let's take this as example 1, and we'll take this equation here, calcium. We'll take this compound, nitrogen, oxygen, let's put that one there, and let's have a sodium. This gives us NaNO3 plus Ca plus calcium. Okay, so we can see here that this equation is not balanced. From the outset, you can see that you have more oxygens on the left-hand side, so let's identify our directions, the sides that we're dealing with. So we have the left-hand side here, and we've got the right-hand side here. Now, you can all automatically see that the number of atoms for each type of atom, i.e. each element, does not balance out for the left-hand side and the right-hand side. So before we start doing anything, let's see what we have from this equation. So we can say that we have the elements. So let's list the elements that we have. We have calcium, we have nitrogen, we have oxygen, and we have sodium. Now, let's list the number of atoms that we have for each type of atom, i.e. each element, on each side of the equation. So calcium. Here we can see we have one calcium on the left-hand side, one calcium on the right-hand side. So we can write one on the left-hand side, one on the right-hand side. Let's look at nitrogen. Nitrogen, again, we have two on the left-hand side and one on the right-hand side. Now I'll repeat that again. If we look at nitrogen, we have nitrogen in brackets. It's attached to oxygen, and it's attached to 3 oxygens, but it's in brackets. Now, the same principles of mathematics apply, where whatever's in the brackets and you've got something outside of the brackets, you need to multiply everything that's within the brackets by whatever is outside. So what is outside? We have this 2 here, and nitrogen is contained within the brackets. So everything inside the brackets, that's including nitrogen, and if we're just focusing on nitrogen, we need to be aware of this, that we have 2 nitrogens. So we have 2 nitrogens on the left-hand side. Now let's move to the right-hand side. How many nitrogens do we have? We have 1. Now, oxygen. Let's look at oxygen. On the left-hand side, we have 2 outside the bracket. That's fine. We've already acknowledged that. How many oxygens do we have inside the bracket? 3. So this gives us a total of 6 oxygens on the left-hand side. Now let's move on to the right-hand side. Right-hand side of the equation, we have simply got 3 oxygens as denoted by the subscript. So we put down 3. Let's move on to sodium. Sodium, left-hand side, 1. We know it's 1 because there's no coefficient, and if there's no coefficient in a chemical equation, we represent that as 1. We move on to the right-hand side. Again, there is no coefficient there beside the sodium, so we represent that as 1 also. So, from this, we can see that our calciums here are balanced. Our nitrogens are not balanced. Our oxygens are also not balanced. Our sodiums are balanced. So we have some work to do. We need to bring up our nitrogens and oxygens. Now be aware that as you start using whole numbers to multiply up with the coefficients, you may end up changing the calcium numbers and the sodium numbers, which are already balanced. This does not matter as long as they are equal. They are still keeping the same amount on the left-hand side and the right-hand side, because sometimes to get the nitrogen and oxygen to an acceptable balanced number, the already balanced numbers or balanced atoms may change. That doesn't matter as long as at the end result you have the smallest possible whole number coefficient representation for each product or compound in your equation. All right, so what do we do now? How do we go about balancing this? So, since we've now identified what is on the left-hand side of the equation and right-hand side of the equation, and determined that this equation is not balanced, we take our first attempt or first step in trying to balance this equation. Now, keep in mind, when we come to balancing chemical equations, you will need to take multiple steps. Now, the steps that I'm going to take, it's going to be very cumbersome because I'm going to outline each step as I'm doing it. As you practice balancing chemical equations, and we are going to do quite a few practice questions on this, you will be able to do this without having to do this whole process which I'm showing you now. However, as you are building up your confidence in balancing equations, I want you to tackle the questions as the way I'm setting it out now. Now, as you become more expert in balancing equations, by the time you do your GCSE exams, you will not need to set it out like this all the time, because you will be able to balance, then you'll be able to play around with the numbers and manipulate the numbers with much more confidence and ease. However, I'm showing you the steps which will always help you in terms of not making a mistake. All right, so let's go on to our next step here. Let's tackle the nitrogen atoms. So we can see we have 2 nitrogens on the left-hand side and 1 nitrogen on the right-hand side. So let's try and rectify this by putting the smallest possible number, whole number, to bring this up. So let's just put 2 nitrogens. So we put a 2 here, and that means that we have now 2 sodiums, 2 nitrogens, and 6 oxygens for this particular compound, which I have put the coefficient of 2 next to. So this changes things slightly, and we have to now represent that change in our little chart. So on the right-hand side now, we no longer have 1 nitrogen, we have 2. This means this is now balanced in terms of the nitrogen. However, that coefficient of 2 is attached for sodium, nitrogen, and oxygen, that compound there. So this means it changes now the number of sodiums we have. This is not a problem. We just state that change and then we move on. So we have 2 sodiums here and 1 on the left-hand side. So this is no longer balanced. So we just keep a note of it, that this is no longer balanced. Now, our oxygen, because oxygen is also attached to that compound, we have 6 on the left-hand side, and now if we look at this number, we have 2 coefficients, the coefficient of 2, so 2 times the subscript 3 gives us 6. So we have 6 oxygens on the right-hand side now. So we have 6 on the left-hand side and 6 on the right-hand side. So now our oxygens are balanced. However, we have an issue now with the sodium, because the sodium is no longer balanced. So if I just take another color, just to make it more apparent, we have to now balance the sodium. Sodium on the right-hand side is 2, sodium on the left-hand side is 1. So let's take the smallest possible coefficient that we can take, and if we need to, we'll move up. So what can we do on the left-hand side to make it balanced to the right-hand side? We put a 2 here. So by putting the 2 on the sodium, we now have to represent that change in our chart. So we can say now that there are 2 sodiums on the left-hand side. And if we compare that to the right-hand side, there are also 2 sodiums. So now we can confidently say that the sodiums are now balanced. And if we take a quick glance now at the atoms and elements on the left and right-hand side, we can see that they all now balance. The calcium is balanced, the nitrogen is balanced, the oxygen is balanced, and the sodium has also balanced out. So now we have a balanced chemical equation. What I want you to do now is, using the method that I have just explained, I want you to tackle these 3 task questions. Now, there's 3 parts of this. There's A, B, and C. Now, I'm hoping you will spot the equation that you would have already come across, probably at key stage 3. I won't tell you that equation right now. I'm hoping you'll be able to spot that equation when you look at each one carefully. So what I want you to do now is pause the video, and I want you to attempt each question and use the steps that we have just described, that I've just described, and I want you to attempt these questions. So you can pause it here, attempt each question, and see if you can get the balanced equation. I will show you the solutions just afterwards. Okay, so I'm hoping that you have attempted each of the 3 questions, and these are the solutions. So here you can see the solutions to A, B, and C. And the equation that I was hoping that you would spot was the third one for C, which was the photosynthesis equation, the equation for photosynthesis. And this can be, the reason I've put it here is because it is a question that can be assessed both in biology and chemistry. So just be aware of that. By learning this equation, you help yourself out in biology and chemistry. Okay, if you struggled with these 3, A, B, and C, ask me in class or at lunchtime or break time, and we will go over more balancing equations. So if you struggled with these 3 equations, you were not able to get the answers, let me know when you come back to class. So this is example 2. For those of you that struggled with the 3 questions, this is a bit more of an explanation of the breakdown of how we balance equations. So this is just to reinforce the concept if you struggled with the 3 example questions, the 3 sample questions. So this is example 2. So let's take the same process as previously. So let's identify how many atoms of each type we have on the left-hand side and the right-hand side. So potassium, we have 1 on the left-hand side. On the right-hand side, we also have 1. Hydrogen, on the left-hand side, we have 2. On the right-hand side, we have 3. Oxygen, on the left-hand side, we have 1. And on the right-hand side, we have 1 here as well. Now, we can straight away see that this is not balanced, specifically in the area of the hydrogen atoms. So, actually, let's identify it. So we know here, this is not balanced, this is balanced, and this is balanced. On our official run, on our first run through, we have identified the problem existing at the hydrogens. So let's try and correct this on our second round. So let's take the second step and try and correct this, the imbalance. So we say, let's put, what's the quickest way to have our whole number and also the simplest whole number, the smallest whole number coefficient that we can add here that would make things work? Let's put a 2 here. Okay, now, if we had put a 2 here, we have now 4 hydrogens on the left-hand side, and we still have 3 hydrogens on the right-hand side. Does this change anything else? Yes, it changes the oxygen. So we now have 2 oxygens on the left-hand side. So now this is no longer balanced. So let's move over to the oxygen. Because now, if we look at the left-hand side, we have 2 oxygens present and 1 oxygen present on the right-hand side. So again, let's try and take the smallest whole number coefficient possible, and let's put a 2 here. So now we have 2 oxygens on the right-hand side. This now makes it balanced for the oxygen. Has it done anything to the hydrogen? Yes. It's now made 2 hydrogen. So if we had 2, if we just take this compound here, we are looking at 2 hydrogens plus another 2 hydrogens there. So now we have 4. So this is now balanced. And what about the potassiums? See, as of now, the potassium on the right-hand side stands at 2, and it stands at 1 on the left-hand side. So this one is no longer balanced. So we need another step. We need to go for our third step. So we have to now try and make the potassiums balance. What's the smallest number, the simplest step, smallest whole number that we can actually take to this equation to make potassiums balance? We simply have to put a 2 here. So now this becomes 2 here. So now when we look back at our chart, there are 2 potassiums on the left-hand side, 2 potassiums on the right-hand side. So now we can say this is balanced. Hydrogens, 4 on the left-hand side, 4 on the right-hand side. We can keep that as balanced. Oxygen, 2 on the left-hand side, 2 on the right-hand side. It is balanced. So this equation now is fully balanced. All right. Okay, so that was just another worked example. Now, there are a few points. If you struggled with that, we can break it down further into 4 concise steps. Now, so if you take a note of these concise steps, this will help you in terms of balancing equations. Now, if the number of each atom on either side is the same, you're all good and the equation is balanced. So sometimes you may get an equation, they may ask you to balance it, do a check first, and sometimes you may not need to balance it and it is already balanced. If the number of each atom, so this is the second point, if the number of each atom on either side is not the same, you need to use big numbers in front of each element or compound to even them out. And remember what I said, take the smallest whole number coefficient if possible at all times. Every time, this is the third point, every time you add a big number, you multiply the whole compound by that number. And so you adjust the numbers in the table accordingly. And then the last point, repeat until you have the same number of every atom, every type of atom on the left-hand side and the right-hand side of the equation.